Hey everybody, welcome to the Chapter 5 guided problems. I'll just jump right in. So the first one is an expected monetary value, or EMV problem. These are, I think people think they're harder than they are, and so it confuses them, not because of the difficulty, but because the simplicity actually. So a candy company developed a new consumer product that is expected to earn $4,000 in a profit each year if demand is low, $20,000 if demand is high, and $31,000 if, oh, I'm sorry, $20,000 if it's moderate, and $31,000 if demand is high. The probability of the low, moderate, and high is 30, 45, and 25 respectively. Determine the expected monetary value for the new product. So honestly, all we do is we take the value if it's low, moderate, high. Again, 4,000 in profit if it's low, 20,000 if it's moderate, and 31,000 if it's high. I'll tell Excel that these are dollars. And then, so this is the profit and the probability. The probability of low is 30% or 0.3, moderate 0.45 or 45%, and high 0.25. And then we just multiply it out. So the profit times the profitability. Do that for all three of them. And our expected monetary value is simply the sum, or 17,950. Piece of cake. All right, our second question is a binomial probability distribution. We can tell it's binomial because, well, let me just read through it and I'll tell you why. The government's Department of Transportation reported in 2009, Airline A led all domestic airlines in on-time arrivals for domestic flights with a rate of 83.3%. Complete the parts A through E below. So we know it's binomial because flights could either be on time or not on time, and that's it. So it's either either they were on time or not. That's only two options. That's a binomial probability. So the first thing we need to do is kind of collect the data. We're going to need to work this out, and to do that, we're going to need N for the number of trials. We're going to have P for the probability of success in any given trial. And we may need Q, which is the probability of failure. So N, number of trials. So it says, what is the probability that in the next 6 flights, exactly 4 flights will be on time? So the number of trials is 6. Our probability of success is 0.833, or 83.3%. And then our Q, our probability of failure, is 1 minus our probability of success. Since things can only be a success or a failure, that's our only, whoops, it thinks I'm doing dollars. All right. So the probability of that in the next 6 flights, 4 flights will be on time. So we're going to use, I'm just going to call this one A. We're going to use a function in Excel called binom.dist, which returns the probability of a binomial distribution given us a few things. And the things it gives us are, or the information we need to give it is the number of successes. So for this problem, 4 successes out of 6 total trials. Our probability of success is 0.833. And then we have to tell it whether it's cumulative or not. So cumulative means the probability of multiple values. So if it had said 4 or fewer flights being on time, that would be a cumulative. In this case, it says exactly 4. So that's not multiple, it's just a single one. So we're going to say our cumulative is false. Oops, sorry, this still thinks that we're trying to do dollars, probably from my last problem I worked out. and it asks for 4 decimal places, so I'm going to go ahead and tell Excel, give us 4 decimals. So B is, what is the probability that in the next 6 flights 2 or fewer? So now we're going to say this equals binom.dist. Number of successes in this case is 2. Number of trials is still 6. Our probability of success is still 0.833. But now our cumulative is true because we want the probability of getting 2 or fewer. So 2 or 1 or 0, right? That's so when we say cumulative, it means look at the probability of this number and everything lower or to the left of that number. You see that's quite a bit lower, 0.088. Oh, 0088. Aha. There we go. So see, what is the probability that in the next 6 flights at least 4 will be on time? So this could be confusing because at least 4, remember if we do cumulative, it gives us the probability of anything being less than a certain number. So out of 6, if we say at least 4, we want the probability that 4, 5, or 6 are on time. So the way we have to do this is we have to tell Excel this equals binom.dist. For the number of successes, in this case, I'm going to use 3. And I'll tell you why in a minute. Number of trials is still 6. Our probability of success is still 0.833, and our cumulative is still true. So if I do this, it's going to return the probability of getting 3 or fewer flights on time, 3, 2, or 1. And our real answer for 4 or greater than would be 1 minus this number. Why? Because there's 100% probability that we're going to have either 6, 5, 4, 3, 2, 1, or 0 flights on time. 100% probability. So if we need to know the probability of having 4 or greater, then the only way we can do that using Excel is to find the probability of getting 3 or fewer and then subtracting that number from 1. So the probability is 0.9. I better get some more decimals here. 0.9374. That it will be 4 or greater. All right. The mean. So to find the mean, all we do is the formula for that is NP, or the number of trials times the probability of success. And then to find the standard deviation, the formula for that is the square root of NPQ. So equals the square root of N, which is the number of trials, times P, which is the probability of success, times Q, which is the probability of failure. There's our standard deviation. And that's it for question number 2. Sorry, I lied to you. That wasn't it for question number 2. There was still part E. So here it is, and this just wants us to construct a histogram. We could use the technology to construct a histogram, or we can just use kind of common sense and look at it and say, okay, what's the probability? So this one's wrong because here the probability drops from 0, 1 to 2 to 3, and we already saw that the probability actually climbs. Since 83% of them have been on time, it's likely, and that we have a mean of around 4.98 or 5, that our high point is going to be around 5. So we can just look here and see that the highest point is around 5. And then we know this one is out because this says the probability of 6 being on time is like 100%, and we know that that's not true. That's my process for going through. So there is truly the end of question number 2. All right, and our third question, we're going to consider a Poisson probability. Remember to recognize a Poisson probability. They always measure a certain number of occurrences of something over a certain period of time, usually, or over some other interval, like distance. This one doesn't really get into the story part of it. That's one way if you're looking and trying to tell is something binomial. Binomial would be something that measures successes or failures. Either something is a success or it's a failure. It's binomial in nature. But with a Poisson, you'll be measuring some occurrences over time or occurrences over distance. And that's what we use Poisson probability distributions for. Anyway, so consider the Poisson probability distribution with a lambda of 3.3. That's our mean. Determine the following probabilities. A is the probability that something is exactly 5 occurrences happening. So we're going to use the function equals Poisson dot dist. That asks for x. In this case, x is 5 occurrences. Asks for the mean, which is 3.3. And cumulative, again, if we put true, then we're saying that'd be like asking what's the probability that it is 5 or fewer occurrences, 5, 4, 3, 2, 1, or 0. So if we say false, then we're saying what's the probability that it is exactly 5? Ooh, look, I almost made a mistake. It should be 3.3. And I spelled false wrong. I'm just making lots of mistakes. So that gives our probability. It asks for 4 decimal places, so I'm just going to set Excel, maybe. 4 decimals. The probability of 5 occurrences is 0.1203. The probability of more than 6 occurrences, so in this case, if it's more than 6, again, when we use Excel, we're finding the probability of that number or fewer. So if we do more than 6, we can say this equals Poisson dist. So our x will be 6. Our mean will be 3.3. And our cumulative in this case will be true. And this will return the probability of 6 or fewer occurrences being of 6 or fewer occurrences. So to find our answer, we have to take 1 minus that probability. And that's the probability of greater than or more than 6. And then C, probability of 3 or fewer occurrences equals Poisson. Here x is 3, mean is 3.3, cumulative is true. This will return the probability of getting 3 occurrences or fewer. .5803. So something that confuses people often on problems like this is they don't know whether to include, like here I included 6, and it was because it was more than 6 occurrences. So we wanted to find the probability of 6 or fewer, and then 1 minus that would give us greater than 6, which is what it asked for. Here it says 3 or fewer, so I use the number 3, and that gives me the probability of 3 or fewer. That gets confusing. You just kind of have to ask yourself, what is it asking for, and how do I respond to it? So our last question is about a hypergeometric probability distribution. And hypergeometric distributions are used when we have when we're trying to take a small sample out of a larger population, and we're doing it without replacement. So that's, again, just trying to kind of tell you the difference between the 3 that we use. Binomial is the probability when we have successes or failures. And the Poisson then is when we have the number of occurrences, usually over time or distance. And then the third is hypergeometric. and that is when we're dealing with samples being taken out of a larger population without replacement. So the easiest way for me when I set these up is just to put all my variables over here. So my number X, that's going to be my successes from the sample, which I don't have yet. My number N is the number of trials in the sample. Sorry, I don't like all these decimals being here for this part. Our big R, that is the number of successes in the population. In this case, our big R is 4. That's given to us. And our big N are the number of trials, if you will, in the population. All right. So to do a hypergeometric probability distribution, I'm going to create a little calculator here. Not really. I'm just going to say this equals HYPEGEOM, hypgeom. Not E, just HYPGEOM dot DIST. And then if you read this, it says sample successes, comma, the number in the sample, comma, population successes, comma, number in the population, comma, cumulative. So what I'm going to do is I'm going to just do X, that's my sample successes, my number in the sample, which is 3, my population successes, and my number in the population, and then the cumulative. Again, because this one is x equals 0, we're going to say it's false. We want just the probability that x equals 0. And when we do this, it's going to give us an answer, but we still have to put in our x. In this case, x equals 0. So the answer we get is 0.0714. What's cool about doing it this way is I can leave everything else the same, and I could just keep using this to find my answer instead of doing the ABC. So for example, what's the probability that x is greater than 1? So now I can put 1 here, and I can change this to true. And that answer it gives me is the probability that x is less than 1. So it's either, so in essence, the probability that it's 0. And then I can do 1 minus this, which I don't really have to do this time because 1 minus 0.5 is still 0.5. Here, what's the probability that x is less than 3? So remember, if we put our x as 3, it would be telling us the probability that x is a 3, a 2, or a 1, or a 0. We don't want that. We want the probability that x is a 2, or a 1, or a 0 is less than 3. That's why I plugged in 2. And there our probability is 0.9286. All right, so the mean of the distribution. The formula for the mean, you can find that in your book, is our little n times our big R divided by our big N, okay? Or in other words, the number of trials times the number of successes in the population divided by the number of the successes in the population. That gives us our mean. And then our standard deviation of the distribution, this is a little bit more involved. I mean, it's still just a formula, but you got to do the formula. So the formula for the standard deviation is the square root of got the little n times the big R times big N minus big R, or big N minus our big R. And then all of this, so I'm actually going to have to put another set of parentheses in there. All of this divided by big N squared. So let's see, we want the square root and then all of this, we just have to make sure we close this right. I think that will do it. And we multiply that times the square root of big N minus little n, big N minus little n, divided by big N minus 1. Let's see if that's right. Uh-oh, I did something wrong. So that's the challenge when we're doing these big formulas. It's easy to mess something up in Excel. So let's see, I have to check it again. So it's the square root. Oh, here's where I messed it up when I clicked off that cell. So it shouldn't be F10. It should be, it should just be out of there. That's our little n times our big R. That should do it, hopefully. Let's see if it's right or if I need to redo it. 0.091, no, 2. All right, sorry, I'm not going to re-record this whole video. I'm going to instead redo this last little part. So I'm sorry if I screwed you up. Let's take a look at how I did this. In fact, I'm just going to delete it and try again because I tried this several times and I've gotten it right before. So it's probably just an error on my part. So this is the square root of our little n times our big R. That's multiplied by our big N minus our big R. And that whole thing is divided by big N squared. And we want this to be the square root of the whole thing. That's probably where I messed it up before. All right, and then we multiply this by square root of our big N minus our little n, divided by our big N, whoops, our big N minus 1. And that gives me 0.7319. I bet you that's right. Oh, 3 decimal places. 0.732. Okay, finally. All right. Well, thank you for being patient through that last part, and hopefully the way I set that up will help you set it up for your homework and help you be successful. Good luck in the rest of the chapter.